So for this video, I'll be discussing determinants, its theorems, minors, and cofactors, expansion of determinants by minors. For a brief introduction of determinants, a determinant is a number associated with a square matrix, and is useful for solving and analyzing linear equation. It is considered to be a scalar value that is a function of the entries of a square matrix. For the difference between determinants and matrices, determinants are expressed in a pair of vertical lines, while matrices are expressed in brackets, as seen here. Moreover, determinants are the rows and columns of determinants should be equal, while for matrices, it may or may not be equal, as seen here. For determinants of order 2 or second order determinants, let's consider this 2 by 2 matrix. We can solve this through these steps. We multiply the diagonals from the top left to the bottom right, a sub 1 1 times a sub 2 2, subtracted 2 from the bottom left multiplied to the top right, a sub 2 1 times a sub 1 2. Let's have an example. Find the determinant of the given matrix below. Let's consider this 2 by 2 matrix. So let's follow our diagonal pattern. From top left to bottom right, that's 3 times 2 minus 1 times 4, following our diagonal pattern. And that will be equal to 2. Next, for the determinants of order 3, let's consider this 2 by 2, 3 by 3 matrix. First, we get the first two columns of the original matrix and multiply it to the original matrix. As seen here, we took the first two columns and multiplied to the original matrix. Then we can follow our diagonal pattern. A sub 1 1 times a sub 2 2 times 3 3, which is this one, plus a sub 1 2 times a sub 2 3 times a sub 3 1, plus a sub 1 3 times a sub 2 1 times a sub 3 2. Next, from the lower left to the top right, a sub 3 1 times a sub 2 2 times a sub 1 3, minus a sub 3 2 times a sub 2 3 times a sub 1 1, a sub 3 3 times a sub 2 1 times a sub 1 2. Let's have an example. Find the determinant of the given matrix below. So for the first step, let's get the first two columns and multiply to the original one. So the first two columns will be 6, 5, negative 2, 3, and 1, 4, which is multiplied to the original matrix. To acquire the determinant, we can then follow our diagonal pattern. So that will be 6 times 3 times 3, plus 5 times 1 times 1, plus 0 times negative 2 times 4. Next, from lower left to top right, 1 minus 1 times 3 times 0, minus 4 times 1 times 6, minus 3 times negative 2 times 5. 6 times 3 times 3 is 54, 5 times 1 times 1 is 5, this will be 0, this will be 0, 4 times 1 times 6 is negative 24, minus 24, 3 times negative 2 times 5 is 30, which gives us 65. So van der Monde determinant is a special type of determinant in which the first column has value of all 1, and we can follow along with this formula. So let's have this example. We can notice that all its values from the first column is 1. So let's try to solve this. B minus A, our B is 3, our A is 1. 3 minus 1. C minus A, our C is 4, our A is 1. That's 4 minus 1. C minus B, our C is 4, our B is 3. That's 4 minus 3. Multiply all of them together, 2 times 3 times 1, it gives us 6. Proceeding to the theorems of determinants. For the first theorem, the N Factorial is the number of the terms in the expansion of a determinant order of n, where the second order has the number of terms 2 factorial, 3 factorial, and 4 number of terms 4 factorial, and so on, which was explained earlier for the determinants of order 2 and 3. Proceeding to the second theorem, the value of the determinants is unaffected if the matching rows and columns are interchanged. Let's say for this given example, let's interchange the matching rows and columns. So for row 1, it became column 1. For row 2, it became column 2. For row 3, it became column 3. We interchanged them equally. Now if we solve for this, 3 by 3 matrix for the determinant, we will get the value of this, negative 77. And if we also solve this, we will also get the same value of negative 77, following the second theorem's principle. Proceeding to the third theorem, if any two columns or rows of a determinant are interchanged, the sign of the determinant is changed. Let's look at this example. So given here, we have this 3 by 3 matrix. And if we solve this, it says that it has this answer. A equals this equation. However, if we interchange row 3 and row 1, our row 3 becomes row 1. So GHI goes to row 1. ABC goes to row 3. If we interchange them and solve for the determinant of this 3 by 3 matrix, we will get the opposite sign of the original 3 by 3 matrix. So that proves the third theorem, which changes the signs once we interchange some rows or columns. For the fourth theorem, when all elements in a determinant, column or row, are 0, it is null. Let's observe this example. We observe that the column 3 has all values of 0, which means the answer is null or 0. Same thing with here. Row 1 consists of all zeros, which means the value is 0 or null. For the fifth theorem, when a determinant's two columns or rows have identical or proportionate elements, its value is 0. Let's say, given this example, we have identical elements in row 1 and in row 3, which gives us the value of 0. Now, for this example, we can see that column 2 and column 3 are proportionate, since 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, which gives us a proportionate elements and has now the value 0. For the sixth theorem, which is the last theorem, if each element of a column or row in a determinant is multiplied by the same number. Let's try this example. So for this 3 by 3 matrix, if we were to solve this using our diagonal patterns, we will get the value of 5. Now, let's try multiplying the second row by 3. So this is the second row. Let's multiply it by 3. We get 3 times 1, 3. 3 times negative 1, negative 3. 3 times negative 1, negative 3. Now, if we were to solve this, we will get the value of 15. But since we multiplied 3 to the second row, we also multiply 3 in this part of the equation. So that's 3 times a. So 15 equals 3 times a. Divide both sides. Will give us a equals 5, which is the same as the original matrix. Same thing goes here. If we multiply the first column by 5, we will get 25. And of course, we multiply 5 to the other side, and 25 divided by 5, cancel. A will be equal to 5 as well, as the same as the original 1. So, for minors and cofactors, it's considered to be helpful in solving determinants of large matrices, 4 by 4, 5 by 5, and 6 by 6. So here, presented with the formula of cofactors, we have negative 1 raised to I plus j times mij, which is the minor. I is the number of rows, and j is the number of, or the column number. So let's identify the steps. So let the element to be used in row 1, column 1, which is a sub 1, 1. Let's say our element is a sub 1, 1. Second step, we cross out the elements that come along with the rows and columns. So we cancel or eliminate its row and its column, leaving us with this 2 by 2 matrix, a sub 2, 2, 2, 3, 3, 2, 3, 3, which is this one. Now, acquiring the minor, we can have our diagonal pattern, which is this one. We can then have this equation, which is our minor. Now, lastly, for solving for our cofactor, we can follow the formula in which I is the row number and j is the column number. So it's negative 1 raised to 1 plus 1 is 1, and times our minor, which is this one. So 1 times our minor will give us this answer of cofactor. Let's have an example. So find the minor and cofactor for the value 6. So 6 is located here. Then we eliminate its row, eliminate its column. we are left with 1, 2, 7, 8 with this 2 by 2 matrix. We can then solve by using our diagonal pattern, 1 times 8 minus 7 times 2, which gives us a minor of -6. For the cofactor following our formula, I is our row number, which is 2. 3 is our column number, which is 3. So -1 raised to 2 plus 3, so that's -1 raised to 5 times our minor. So that will be equal to 6. So for the expansion of determinants by minors, it is computed by continuously breaking the matrices down into smaller matrices until the matrix is 2 by 2. And we follow along with this golden rule of signs in which we solve the equations. We first must know the minors. So let's consider this 3 by 3 matrix. So let's say we'll be expanding row 1. And in this way, we can list them down, a sub 1, 1, following our golden rules of signs, positive, negative, a sub 1, 2, plus a sub 1, 3. Next, we can follow along with the rules of minors in performing and creating these 2 by 2 matrices. Let's have an example. For this example, let's say we're going to expand row 1. So we'll be listing, following along with the golden rule of signs, 5, -0, +2. So first 5, we eliminate its row and its column, following the rule of minors. In this way, we are left with 3, -1, 6, 2. Next, 0. We eliminate its row, its column. We are left with 7, -1, 4, 2, just this one. Next is 2. We eliminate its row, its column, and we are left with 7, 3, 4, 6, which is this one. Now we can perform the diagonal pattern for solving the 2 by 2 matrices of determinants. And we can follow along with this equation. Since this is 0, automatically this is 0. So we are left with this one. So 3 times 2 times minus 6 times -1, that's 12 times 5. 7 times 6 minus 4 times 3, that's 30 times 2. Adding them all up together, we got 20. Now, let's have the same example, but let's expand a different column or row. Let's say we're going to expand the second column, 0, 3, 6. So following along with the signs, the second column, negative, positive, negative, we got -0, +3, and -6. So let's first start with 0, eliminate its row, its column, and we are left with 7, -1, 4, 2. Next for 3, let's eliminate its row, its column, so we're left with 5, 4, 2, 2, which is this one. Next is 6, let's eliminate its row, its column, and we are left with 5, 7, 2, -1. So following our diagonal patterns again for solving the determinants for 2 by 2 matrices, so that will, since this is 0, this is also 0, so we are left with this one. 5 times 2 minus 4 times 2, which is 2, and 5 times -1 minus 7 times 2 times 6, that's positive. Since this is negative, this is positive 114. 3 times 2, that's 6, plus positive 114. We'll also get the same answer, which is 120. So we just showed another method of expanding through the expansion of determinants by minors. And that's it for my video. Thank you for watching.